Hello, everybody. So this is a lecture on working with proportions. Sometimes we work with proportions instead of with raw data. I mean, we can actually just use proportions and test hypotheses with it. So just recall that the binomial distribution provides probability associated with a given number of successes in n independent Bernoulli trials. Remember, a Bernoulli trial is a trial in which there are two possible outcomes, success or failure. And remember, we also use the word success as not in a qualitative sense, but more as is success at whatever we're looking for. Like it could be success for the number of heads when you flip a coin 10 times, how many heads you get, or it could be how many cases of COVID there are. So we just use success to mark whatever we're looking at whatever our variable or outcome of interest is. If the probability of successes is constant from one Bernoulli trial to the other, we can count the number of successes in a series of n independent Bernoulli trials, and that distribution of the number of successes it follows a a binomial distribution. And we can convert the number of successes in n Bernoulli trials in a sample to a proportion. So dividing, this is your equation for a proportion. You just divide the number of successes out of those n Bernoulli trials, and we get an estimate, this little hat over here. We get an estimate of the population proportion P. Now, the next thing is to determine, can we assume that we have a normal, or at least approximate a normal distribution with our binomial? To do so, we need to have a large enough sample. And there are so many different criteria for what's considered a large enough sample size, right? Usually it's like having a large sample and a probability around 0.5, probability of success around 0.5. But there's all these other heuristics like n times p, the number of successes, number of trials, n times the probability of success should be greater than 10. It's Piper in the background, my rainbow lorikeet parrot. He's just trying to get involved. He's actually, so each one of those is a success, right? So we can count how many successes he has in like an infinite number of Bernoulli trials, because he probably won't shut up during the whole time. And then here, and also n times 1 minus p. This is the probability of failure is greater than 10. So if we meet these, this is from the chapter that I wrote. There's all these different heuristics about what you should use, and it seems like 10 to me makes sense as a compromise. A lot of people say np greater than 5, n times 1 minus p greater than 5, but I looked at some simulation studies, and that wasn't necessarily ideal. So it looks like 10 is good, a good compromise. Of course, if you have a really large sample size and your probability is around 0.5, no worries, right? Excuse me. The conditions met, then the sampling distribution of a binomial random variable follows an approximately normal distribution with a mean mu, and the me's mu, and mu is again is the mean, and it's where the expected value is n times p, right? And this is its standard deviation, the square root of np q. And sometimes we use q instead of 1 minus p. You may have seen that, because people don't want to always write 1 minus p for the probability of failure. So they'll say let q equal 1 minus p. But so it's np 1 minus p. If we want the variance, we square that puppy. Okay, we can use this information to identify the observed proportion of successes and then compare an observed proportion to a population proportion using a z-test as the expected proportion. Right here is a good estimator of the population proportion, right? So this is actually showing you how we derive it, right? So you take this is as we said here, this is the mean, right? The mean, excuse me, number. But of course, dividing by n, the n's cancel out, and we get the sample proportion is a great estimate of the population proportion, right? All right, the standard deviation for the proportion of successes, here is sigma NP divides a square root of NP 1 minus P divided by N. And then we can just like, play around with this a little bit and reduce it to the square root of P 1 minus P divided by N. And our test statistic is then, because again, we're dividing by this standard deviation here, is the difference between the two, between our estimate and then the population proportion. So it's a Z statistic here. So we standardize it. And of course, as we know that once we standardize something, the central limit theorem applies to it. Okay, it has to be standardized for the central limit theorem to apply. A lot of people assume it's just the sampling distribution, but it's not. It's actually the standardized version to which the central limit theorem applies. So central limit theorem means as the sample size increases towards infinity, the distribution of whatever variable converges to normality. So it has to be standardized for that to occur. There's some good sites for that if you want to look that up. Here's a textbook example. In this example, the researchers were exploring, this is from a study that I actually worked on with a couple of people. They were looking at some gastrointestinal bleeding technology using a visual capsule endoscopy. So it's like having a little tiny submarine in a pill, where you swallow the pill, and then there's little people inside the submarine trying to detect bleeding. So they wanted to detect rebleeds among patients with diagnosed obscure occult gastrointestinal bleeding. So that's a mouthful there, right? So, this is one of the tests we use, like one of the less invasive tests that's used for detecting colon cancer, right? You look for bleeding, intestinal bleeding. So it's like a stool test. So I guess they're looking at rebleeds. This is a good method though, right? Using a little tiny pill with a camera in it. So upon completing data collection, the researchers found that the proportion of rebleeds after the VCE procedure among the 314 patients sampled was 0.089 or 8.9%. They noted that the population proportion from a recent meta-analysis they reviewed is 20%, right? So this is our population proportion. This is our sample proportion. Remember, the sample proportion is supposed to be an estimate of the population proportion, right? So it's a really good estimate. It's called an unbiased estimate, right? It's a good estimate, but it's not always going to be perfect. It's just an estimate. Is the proportion of rebleeds observed by the research team different from the population proportion? All right, let's check. So the null and the alternate, okay, Piper, thank you. He said, okay. The null and alternative hypotheses are the sample portion is equal to 0.20 and the sample portion is not equal to 0.20, two-tailed test there. Two-tailed because again, we don't specify the direction of the relation. It could have, but whatever. So let's make sure we have sufficient data to use the Z proportions. So we use N times the population proportion, right? That's what the 0 means because it's associated with the hypothesis. The null hypothesis has to be greater than 10, right? As it does this one, right? This is the probability of failure or no rebleed. So here's an example where we qualitatively have like a negative outcome being success, right? Having rebleeds, because you'd like to not have rebleeds. So a success is having rebleeds. So we enter our sample size, N is 314, and our population proportion. What do we get? We get 62.8 and then 251.2. So that obviously we meet the criteria. So we're good. Let's plug our data into the Z equation, right? The Z equation here. We get, what do we get? We get, so this is our standard error in the denominator. And we get minus 4.925. And our p-value is pretty small. There's less than, so I talk about using our Z table So a Z table, you're not going to find a value that large, right? I think the Z tables usually go up to 3 or something like that, or plus or minus 3, and you'd find the probabilities there. But anything at this large or larger, has a very, very small probability. So in this case, it's less than 0.0001. Okay. So because we're dealing with discrete variables and then working with a supposed normal distribution. Well, a normal distribution, using the what did I say? Continuous, a distribution that's more applicable to continuous variables, the normal distribution. And again, we're making this conversion here or from something that's discrete to something that's continuous, right? So we want to do an adjustment here to an adjustment for going from a discrete to continuous distribution. So we'll just add this correction of 0.5. 0.5, it's interesting is because when you think about those bars, the bars are centered on a point, but the bars are usually have a width of 1 unit on the x-axis. So we add this 0.5 here to the proportions to make that correction right here. So this is called a continuity correction. With the continuity correction, let's see what happened. What did we get? We got 4895. What do we have before 4? I mean, didn't make much of a difference here, right? Just a minor difference because it was so large. The difference was so large, we still had a significant finding. Now we're going to add the 95% confidence interval to this. So this is a walled confidence interval. These walled confidence intervals are problematic and they're not ideal. So just got to keep that in mind. We use them just because they're easier to use than using the better confidence intervals, at least in working by hand. I mean, if you're working on a computer, you have access to a variety of different confidence intervals, and I would pick whatever's best for my situation. But working by hand, I just decided to use these because they're easier to calculate. So here we have this walled confidence interval. You have proportion, your sample proportion, and then you have your margin of error here, which again includes some Z value here, some cutoff points for these are. So why the reason we have alpha divided by 2 is because this is a cutoff on the distribution, on the normal distribution, right? So the area between the negative and the positive value here, so it's plus or minus, that's the area that represents confidence for our sample coming from a specific population, or for finding our population or true population value. And this part right here under the radical sign is, well, including the radical sign, this is our standard error. So we just go ahead and do this calculation and we get a value that includes a negative, and for this case you can't get a negative because there aren't any negative proportions. However, this is a problem with this walled confidence interval. So to deal with that, we just set a floor at 0, right? We constrain it to 0. So we've our approximate 95% confidence interval would be 0 to 0.1789. Why are every time I'm sorry, I can't help myself. Why are all the other numbers afraid of 7? Because 7, 8, 9. So yeah, there are better confidence intervals or limits. I mean, confidence intervals that you don't have to deal with this issue. But again, this is easier to calculate by hand. I mean, it doesn't look easy, but it is easier. I do it by Excel probably. For comparing proportions by 2 samples, we also have, I mean, that's something that's not uncommon either. Just like you're comparing, I don't know, 2 groups in any kind of study. A 2002 study, excuse me, compared the incidence proportion, excuse me, incidence proportion of self-reported concussion symptoms in a Canadian university sample of 328 football players and 201 soccer players, right? So American football, right? And soccer. It's just for your FYI, for your information, incidence means new cases, right? That's an epidemiology term, in case you don't know. So new cases. So they found 231 of the football players, 70.4% of the football players reported experiencing concussion symptoms in the previous year compared to 126, 62.7% of soccer players. Using available proportions and sample size, we can assess the difference in proportions for significance. So here's the interesting thing. As long as I know what the sample size is and I know what the proportions are, I can just do these calculations, right? But I don't have to have raw data where I have what I mean by raw data is a spreadsheet with one individual on each, whatever, in each row, and then, different variables, and have to use a statistical computer package or Excel to calculate. I don't need that. I just need, as long as I have the proportions, I'm good. And sample sizes. So I've used this with students who have projects where they want to say compare proportions of, say, homeless people in two different states or something like that. And you can do that. It's so easy. It's awesome. That's why I wrote this chapter in proportions, but some people overuse it. There are other ways to do things too. My son had a course in college where his professor just used proportions for everything. It's like, oh my gosh, there's so many other methods to use out there. But that led me, and working as a tutor, that led me to use proportions elsewhere, or to write this chapter, I should say. So is their sample size large enough? So let's do that. We have to do this for each of the two samples. We use this n times p and then n times 1 minus p criteria. And in both cases, we have massive numbers here, way over 10, so we're good. We can proceed. We write our hypothesis. The sample, the proportion. Notice here that I don't have the little hats here, so because we're making estimates of population values here. So even though we're working at samples, we're thinking population. So proportion among football players is equal to the proportion among soccer players reported concussion symptoms. In this case, I do a one tail. The proportion of football players is greater than soccer players. Okay. So our z-test here for comparing proportions, we have football minus soccer, and then this is our standard error in the denominator. And I have this p with a bar over it. So that's just the number of successes in both conditions divided by that. So it's basically the number of successes. Or in this case, the number of concussions, right? Reported concussion symptoms divided by the total. It's just a proportion, but it's for the total, right? Using these two equations, we get our z value to be massive again, 43.95. So this difference is significant. If we added the continuity correction. So this is from my textbook. So if you're not familiar, I mean, if you don't have the textbook, just make sure you get it. I mean, it's kind of late now for my course. For this course, it's late, but if anybody's watching this from outside of my course, then it's never too late to buy the, I don't know where the textbook is now. Let's see. It's never too late to buy the textbook. There it is. Yeah, there it is. Core statistics, practical knowledge for the health sciences. Yes. Second edition. But anyway, that's page 96. So let's add, so we have this value, we're going to add a walled confidence interval, keeping in mind that this confidence interval can be problematic. Or it could be, there's better confidence intervals to use. But again, I just use this one because it's easier to use. So you have this delta with a hat here. That's the differences in the proportion. Delta is usually used to indicate some kind of a difference. That's just it's just one way to write it. And then with the hat means the proportion, differences in proportions. So we get plus or minus, and we have our z value again. Remember, this is for the cutoff points for our confidence interval divided by n, and then we multiply a time. Yeah, so this is kind of like an adaptation here because obviously we pull the n out of here, right? So, so we can like, there's all these little adaptations we can do to simplify the notation or to make things a little easier for us to calculate. And we get this confidence interval from going from negative 0.00576 to 0.160. So this is telling us that while our difference in proportions is 0.0, our difference in proportion is 0.077. It can be anywhere as small as a negative value, where, in this case, soccer players have higher than higher concussions than football players. So we did football minus soccer up to 0.16. And again, remember that there are better confidence intervals. So I say this is a rough confidence interval, and I used it just to make calculations simple. That was our foray into proportions. All right. I mean, there's much more content available in the chapter, including how to calculate sample sizes. But as far as my students are concerned, this is what I'm focusing on. Okay, because I don't want you to get into too much detail with this chapter, because I mean, there's more than we need here. So we're focusing on this. But for all the rest, anybody else watching this, buy the book, read the chapter, this chapter here, chapter 14, includes a lot of good stuff on proportions, including how to calculate sample size and the such right here. So this is what we were just working on. Right. And please, please, please make sure you subscribe to my channel. Everybody should be subscribing. You want me to bring more good content to you. All right. Thank you very much, everybody. Have a wonderful day.